Mars. Yes, comment?
Wasn't this whole idea of methane on Mars substantially criticized in a recent paper in Icarus by Kevin Zomley and his colleagues? And can you comment on that?
I haven't read Kevin Zomley's recent paper. So, and I don't know what he'd be criticizing. I can say that others in the field just criticize the measurements themselves, not being as clear as they could be or high enough sequence noise.
I can comment.
Oh, good. Okay, someone can comment on it.
Zomley and Moma have talked about it a bit, and basically a lot of the criticisms can be ascribed to artifacts in the instrument itself, and they are valid criticisms. But
They're valid criticisms.
Huh?
You said they were valid criticisms.
Some of them are valid, but some of them, it turns out, are less valid than Zomley originally thought.
So does this mean that, in fact, there's some credibility to the original observations, or that we get to make new observations to determine whether this is true or not?
It does require new observations. I wouldn't say that the criticisms weaken it any more than it already was.
Say again?
I don't think that the criticisms put a big hole in it. It's no more or less credible than it originally was.
We had a conversation before in this outside about when you're looking for a very, very weak signal, there are often systematics that have to be removed or corrected for, and you always run the risk of having your detection be actually an artifact. And I think that's what you're saying, that is what they're arguing about. Now, one kind of thumbs up for this is that it was detected both by ground-based telescopes on Earth and also by spacecraft orbiting Mars. And so their criticism couldn't have been for both of those, unless they were saying
it was mostly, I believe it's the same one. It was for terrestrial isotopes interfering with the observations of Mars. Yeah, and some of those signatures were not, in fact, isotopes in terrestrial. They were artifacts in the instrument.
Thank you very much.
Okay, thanks for that clarification. And we'll see what happens. So I'm glad we had that, because it's always good to know what is super robust and what is not accepted by everybody in the community. So if it is there, let's assume for now that methane is there. Why is it so interesting? It is so interesting because methane's lifetime on Mars, due to photodissociation by the sun, is just a few hundred years. So if there's going to be methane there, it must be produced recently. And that's why it's so interesting. And there's two explanations of where it can come from. Remember before I said it can come from life or it can come from geophysics. And so one explanation is that it comes from water-rock interactions. That's what I was saying before, where you have hot water in the subsurface of Mars in this case, going over cracked rocks and releasing methane gas. It's called serpentinization. So that's a possibility. But that in itself would be interesting. Explanation two is that it's produced by bacteria in regions of liquid water, methanogenesis. So even if there is methane there, we don't know if it's produced by life. We wouldn't know until we could go there and look for either other evidence or find the life itself. But it's still heartening for exoplanets, because this is the kind of thing we would be looking for. Some kind of microbial bacteria that's producing a chemical that shouldn't be there, that has an otherwise very short lifetime in the atmosphere, or is there in some kind of unexplained quantity. Now the difference between what we want to find on exoplanets and this methane on Mars is that the methane on Mars is produced in very tiny quantities. And remember before, one of the takeaway points is that any sign of life in the atmosphere we can see from far away has to be produced in very large quantities. But it also helps with the exoplanet idea that it's ambiguous. First of all, if we can establish that there's methane on Mars, the actual origin of it is ambiguous and we can't attribute it to life necessarily. Nonetheless, I think it's one of the more exciting things that's happened on Mars recently. Now I'm going to briefly mention Europa and Titan, because those are other places in the solar system that people are excited about the idea of finding life on. Here's a beautiful picture of Europa. It has a liquid water beneath a thick ice crust. And actually, people have toyed with the idea of going to Europa, drilling down in that ice, and sending some kind of cryobot after melting through the ice to look around down there. Okay, you can see, yeah, this is just the artist's conception of that. But Europa is kind of interesting. It does have liquid water, that's the ingredient, one of the ingredients for life. And if you take people who really work on Europa and you really push them to say, do they really think there is life down there? They'll actually come and they will admit they believe there is ingredients for life. Whether or not there's life is a whole different story. And there's this whole thing about life. Remember when I showed the electron tower and the different chemicals and the chemical energy gradients, and life is extracting energy from those chemical energy gradients, is that you need to have both chemicals present in this redox reaction. It's one of each side. But if one gets completely used up, you're done. Life can't live there anymore. So one concern is that on Europa, because it has this ice shell, no atmosphere to have any cycling of nutrients, that the problem would be that eventually you'd use everything up and life couldn't survive. But for exoplanets, this kind of moon, this kind of object is not as interesting because there's no atmosphere, there would be no atmospheric biosignatures to detect. Nonetheless, I still wanted to mention Europa as an interesting planet. Titan is the next moon of interest. It's 1.5 times larger than Earth's moon and bigger than Mercury. It has a thick atmosphere of methane and nitrogen and hazes that prevent us from seeing down to the surface. Nevertheless, through Cassini, people have discovered liquid on Titan. So right now, Titan is the only other surface with liquid on its surface. And this isn't liquid water, this is methane and ethane, because Titan is extremely cold at about minus 180 degrees Celsius. So this is really great, and whether or not life is there is a whole other topic. I'm not well versed enough to talk about it. I will say one thing though, and I want to mention briefly this really interesting report by the National Academy of Sciences called The Limits of Organic Life in Planetary Systems. And before this report came out, if you picked up a biology textbook, or you took an astrobiology class, you might have heard the ingredients for life. Liquid water, carbon-based life, an energy source, and Darwinian evolution. And in this book, people got together and they actually gave a new set of what they thought were the requirements. And that is any liquid, where chemicals can dissolve and interact with each other. Not necessarily carbon-based, as long as the temperature was appropriate for covalent bonds between atoms so that complex molecules can form. And the temperature has to be the right temperature so it's not so hot that all those bonds are broken. And then also a source of energy and Darwinian evolution. So with that framework, a biologist might be able to find a way to think about life in these lakes. But the relevant point for exoplanets, because then people will ask me, okay, great, you don't need liquid water. This should change the way you see life on exoplanets. And I want to tell you that, unfortunately, it doesn't really broaden our horizons at all. And the reason for that is I'm showing you a graph now of liquids in a planetary system. So if you take the abundance of elements and they're in chemical equilibrium, what they're most likely to form, and what kind of liquids could exist in abundance on any planet, you come up with a list like this. And this is an interesting list. So you can forget about these y-axis. On the x-axis, it's distance from the primary star. This should be 2004. That'd be funny for 3004. So just look at this. Plain sulfuric acid is something you can have at hot temperatures. Water could span quite a large range, depending on what your atmospheric properties are. This is a log scale, so this is 0.1 astronomical units. 1, that's Earth-Sun distance, 10 times Earth-Sun distance, and 100 times. So then here's the methane, or methane and ethane, and then you can have liquid nitrogen and liquid hydrogen. So one of the points that I like to emphasize is that I don't want to be terracentric and say we must have liquid water. But if you think about where can we detect planets and what distance from the star, that water one is really favorable. If you imagine trying to find a big Titan far from its star, it's so cold, it would be very difficult to see in terms of the radiation that comes out of that planet. So it's just this, I don't know if this happened, I won't say it's one of those strange cosmic coincidences, but I will say liquid water still wins out in terms of abundance of that liquid in a planetary system. Okay, so that finishes the brief tour of the solar system and the 3 places, Mars, Europa, and Titan, that are getting the most interest from astrobiologists. And now we'll turn to the search for life beyond Earth and beyond our planetary system. And the key points here are that there are several key points, and I have 3 slides to make. One is that the exoplanet atmosphere is the only way for us to infer whether or not the planet is habitable or likely inhabited. It's our window into temperatures and habitability indicators and biosignature gases. That was part of the last 2 lectures, that seeing the atmosphere in a planet far away, seeing the gases in the atmosphere, trying to find any gases that shouldn't be there, and trying to infer whether or not those are caused by life. There are 2 other basic assumptions here. And one of them is people like to say, ask about what is life, and there's no really great answer. But for exoplanets, we are lucky because we just forget about that. We do not worry about what life is. We just think about what life does. And life metabolizes and produces byproducts, many of which are gas and can accumulate in an atmosphere. So we're not trying to address what life is. In fact, we have trouble even deciding what a planet is. Remember the thing with Pluto and the high mass planets? So we're not into definitions, we just focus on what it does. And there's one other point I want you to know about, and I really want you to, if you learn anything new, learn this one. And that is, we talked about the kind of terracentrism and thinking about life in the universe. And I saw that I made this Venn diagram here, carbon-based life in here. You could be more general and say you just need water and not necessarily carbon. Or you could move even further out and say, well, we don't need carbon or water, just covalent bonds in some kind of liquid. And then actually, in this broad sense, I see us left with two boxes. And one is this one where we use life uses chemical potential energy, or chemical reactions and makes chemical byproducts. And there's even one more box, actually, all life. I just want you to know this because we're making a very basic assumption that life will always make chemical byproducts from metabolism. That's a basic assumption we're making about all life elsewhere. And this other category could include, for example, mechanical energy. Windmills work, they capture energy from the wind and convert that to energy. But actually, we don't see any life on Earth that uses mechanical energy. So there could be other kinds of life. I can't say if there could be, I'm just saying that we are assuming that life is using chemical potential energy. So those three issues, the fact that we want to look at the atmosphere, that we don't worry about the definition of life, we assume there's metabolism which involves release of gases. Those are our three basic assumptions. And now, sort of for the last 10 minutes, I will talk about my own work on biosignature gases, and I have to warn you that there is no conclusion yet, but I'm still going to give you an interesting overview of where I think this field is going. So from that same report, which I encourage you all to read, you can download it from the website, National Academy's website. I love this part from the introduction, saying nothing would be more tragic in the American exploration of space than to encounter alien life and fail to recognize it. Now they're talking about the search for life on Mars. You can also think about this in terms of the possible search for the shadow biosphere. I think about it because I work on exoplanets for the search for exoplanets. And the serious thing that I think about often is if we can do terrestrial planet finder. Remember when I showed you the big petal when I talked about the external culture? Even with all of that, we have 100 sun-like stars that we have access to. When we want to do the big Earths around the small stars, I hope there's a bunch of those, and I'm not trying to be negative here, I'm just trying to be realistic. We can have a dozen or dozens of those super Earth candidates around M stars. And with the future James Webb Telescope, whenever it finally launches, it could be dozens to hundreds of hours per planet. So it's not going to be easy. We don't know how many candidates we'll have. But I always take this quote seriously because we really need to know what to look for. And if we can't figure out what to look for, we at least need to be prepared that when an unusual gas is found, we have an idea of what to do with it. So I took this seriously, and it's actually taken me a few years to do this, just sort of part-time with my colleagues from the UK, William Baines. And so we have this review paper, and it's called An Astrophysical Review of Earth-Based Metabolic Byproducts. And what we did was we started by looking at redox reactions of all microbial life on Earth and all of the gas byproducts that they produce, to see if any could pop out. Could there be a new biosignature gas that we haven't thought of yet, one that exists on Earth that doesn't fill our atmosphere, but that in another exoplanet could fill the atmosphere and could be detectable? We wouldn't want to find another planet and after all that hard work find an unusual gas and not be able to recognize it as potentially being part of life. So I made this pyramid here. If you were to think of all Earth-based redox metabolic byproducts, you can get this big list here. And if you glance through this, if you work in astronomy, if you glance through this, I can do a quick run through of we have oxygen. That's good. That actually, it's hard to, there are false positives, but it's hard to come up with a case with a false positive that doesn't have another indicator. There's H2, which isn't very useful. It's not, in terms of the spectrum, it doesn't really have a spectrum that's useful. It has this broad infrared collision-induced opacity. It's not useful to detect. Carbon dioxide, non-useful biosignature. It's already in our atmosphere. N2, inert, it's already in our atmosphere, 80% by volume. N2O, that's recognized biosignature. We have these other NO gases. H2S, and CH4, and SO2. Those actually are also produced volcanically. Water vapor, not useful. We already have water vapor. I know I sound really depressed here, but okay, ammonia. Ammonia is a really interesting one. You can show that for ammonia gas, if you have, if ammonia is present in the atmosphere, it's a big deal, because ammonia should be photodissociated with the hydrogen escaping to space. And even if the hydrogen remains, the ammonia ends up going to nitrogen, molecular nitrogen. And you can show that for any planet with liquid water, the temperatures and pressures needed for liquid water, you can't break that nitrogen bond, just kinetically with temperature, pressure, with ambient temperature and pressure. So if you were to see ammonia on a small rocky planet, that would be a really big deal. So that would be what I really like. And I've also actually spent time thinking about the other gases and could they be under some circumstances. I actually have a student who spent a year, well, he spent about a year writing a photochemistry course from scratch with hundreds of reactions. And then he applied it, one of the things he applied it to was, could H2S be a biosignature gas? Even though it's also produced by volcanoes, is there some ratio that you might see H2S and SO2 together that might indicate H2S? It's a very long story behind it. And the answer is that it would be pretty difficult to detect H2S unless it's available in huge quantities. And if it is available in huge quantities, you end up generating cases. And so there may be a kind of very complicated way to try to infer the presence of a lot of H2S, but it's not working out that well.